Hello, ladies and gentlemen. Today we're going to be talking about vertically launched projectiles, which is a fancy way of saying throwing an object up into the air and then catching it on the way back down. So to begin with, what I have here on the left side is an image, different snapshots of an object as it moves up and back down. The first thing I'm going to note is a quick vocab word, one that's not on any test or quiz, but just one that I often say, and that is the apogee. The apogee is the top point of any motion. So when I throw something up, it is the highest point. Now you may have heard the word apex before. An apex is the top of a physical thing, like a mountain, but an apogee is the top of a motion as it comes up and back down. This can be objects thrown straight up and down. This can be objects thrown from side to side with that, famous arc, for example, like a football being thrown. It could also be something like the Earth and the Sun. When the Earth is furthest away from the Sun, we refer to that as the apogee. Now, what we're going to be doing is we're going to be breaking down this motion, talking about what's happening to the displacement, the velocity, and the acceleration, and breaking it in half. So during the first half of the motion, the direction of the motion is upwards. And during the second half, it's back down. I think that's pretty straightforward. The velocity is the same thing. The velocity is the direction in which it's, the speed is, in which way it's moving. And that is, again, up and back down. Now, the magnitude is referring to how fast it's going, and is it increasing or decreasing. Hopefully, remember back from our lab where we have a cart going up and back down the ramp, that as it moves up, that ball is going to be slowing down as it moves up, and then it will be speeding up as it falls back down. And of course, we've thrown things in your life, and that should be somewhat familiar. Now, the acceleration, there's often a misconception of acceleration. People imagine that the acceleration is the same as the velocity, that it's up and back down, but it's not. The acceleration is constant the entire time. It's always going down. The acceleration is caused by gravity pulling it down, so it does not change whether it's the object's going up and going down. And this should make sense from what we understand about acceleration and how it affects velocity. When it's in the opposite direction, or when the velocity is going up, it slows down, which is what we expect. And as it is in the same direction of the acceleration as it's moving down, it's speeding up, which is what we expect. The magnitude of that acceleration is constant, 9.81 meters per second squared if you're on Earth, the entire path. Now, in order to answer a vertically launched projectile question, there's a couple of techniques that I recommend doing. The first and major one is to break down the motion into two halves. It's much easier to answer this problem when you're not talking about the object as it comes up and back down, but instead talking about either the object at the start, up to the top, or from the top back down. It's also important to note that the first and second halves mirror each other. When there's no air resistance, when you throw an object up, you actually catch it at the same speed that you threw it at. And the time it takes to go up is the same as the time it takes to go down. And of course, the distance that it went up is the same as the distance that it went back down if you catch it at the same height. So they're exact mirrors of each other. The only thing that's different between the two is the direction. And speaking of direction, in physics, we have to negate when we have opposite directions as negative numbers. So if we have one thing going up and one thing going down, we have to make one of those directions negative. And the choice is up to you on which direction you want to make negative. So in these questions, when we have objects going up and down, you have to think about, okay, is the velocity in the same direction as the acceleration? Is that in the same direction as the displacement? And things like that. If you get an unexpected negative number, there's a good chance that you weren't thinking about negatives and positives. Let's do an example of one of these questions. Let's say that we have an object that is being thrown up into the air and back down. And up at the top, we have the apogee. Let's say that that object was in the air for 3.2 seconds. We have a couple of questions for how high did it reach and how fast was it thrown at. To start off, I actually want to go over a case where we did not break it down into the two parts. So we're going to see why it's a little bit tougher here and why we're going to get answers that aren't very helpful. And then we'll get into the actual way that we're going to be doing it, which is to break it down into two parts. So let's use this formula. We have the final velocity is equal to the initial velocity. The final velocity squared is equal to the initial velocity squared plus 2AD. Now, because the object is mirrored of each other, the final velocity and the initial velocity are actually going to be the same value of each other. Now they're in opposite directions, but the fact that they're squared actually cancels that factor out. And so what I've done is I simply replace the initial velocity with the final velocity because it's the same. Is equal to 10 meters per second squared. I'm using that instead of 9.81 times the distance. And if I was to solve for this, if I subtract both sides by final velocity squared, I would get 0. And then if I was to divide both sides by 20, of course, I would get a 0 displacement. Now, at first, that seems like, okay, obviously you can't do that, that's wrong. But in fact, that is the correct answer. What we just found there wasn't how high it reached, but we have to think about what points we actually took. When we found the distance here, the fact that I picked the initial at the bottom and the final at the bottom, the thing that I actually figured out was not the distance from how high it went to the top, but instead the displacement between where it was at the top, where it was from the bottom being thrown back down to where I caught it. And if you catch it at the same height you threw it at, the displacement should be 0. So this is actually a correct answer. It's just not useful whatsoever. This is why breaking it down into parts allows you to solve this problem much easier. So let's take a look at how we do that. The key part of this is that we're going to be using the fact that the velocity at the top of the motion is 0. And I apologize, I put meters there. It's meant to be meters per second, of course. So the velocity is 0 meters per second. So you're going to want to quickly adjust that in your notes. And that's the speed at the top. We're going to use that speed to help us out. The other thing that we need to keep in mind is the time it was in the air. If it took 3.2 seconds to go up and back down, we have to remember that it only takes half that time to go from either up to the top or from the top back down. Both of those will take the same amount of time. We just take the time divided by 2. If we do that, we get 1.6. So it took 1.6 seconds to go up, another 1.6 seconds to go down, for a total of 3.2 seconds for the motion. So I'm going to be using El Grande to solve this problem. And I'm going to be plugging in 0 for the initial speed. So what I'm going to do to make my math a little bit easier is I'm going to be using the speed at the top, and I'm going to be talking about the second half of the motion. And what I'm going to be doing is I'm going to be finding the distance from here down to here. And if you actually use the first half of the motion and plugged in the initial value, we don't know what that is yet, but if you did know it and you plugged it in, you would actually get the same answer, which is pretty interesting. But at the top, back down, it starts off at 0. The time it takes is 1.6, because again, we're only doing half the time. And I plugged in all those values of my 10 meters per second squared to make the math a little bit easier. And I get 12.8 meters. If I was concerned about sig figs, well, it would need to be, I guess, 10, but 13, 12.8 is fine. I didn't pay attention to sig figs for this one. So it went from up at the top back down to my hand. It took 12.8 meters of displacement. Now, direction wasn't a big factor here, and that's because everything here is moving in the same direction. 0 doesn't have a direction that we're concerned with. This 10 meters per second is directed downwards, because that's the acceleration. So the displacement that I got is also directed downwards, which works because we went from the top back down. And that is the total height of the ball that it reached. For the next one, we have the VF is equal to VI plus AT. My goal now is to figure out what the final velocity or the initial velocity was. The actual final and the initial, not the velocity at the top, but those. Again, I'm going to be using the half time to do this. I'm going to be plugging in 0 for the initial, so again, I'm using the second half. I find that half more useful. I plugged in my acceleration of 10 meters per second squared, and I plugged in my time of 1.6 seconds. And I should get a final velocity of 16 meters per second. Direction, again, is key. The acceleration was going down, and the final velocity is going down. Now, I want you to think about this for a second. What if I instead use the first half of the motion? What would be different here? The only difference between the first half and the second half is what I consider the initial and the final velocity. If I was to do the first half of the motion, the initial velocity would be the thing I was looking for, and the final velocity would be 0 at the top. And if I was to solve for that initial velocity, I would get the same 16 meters per second. The only difference is I would get it negative. And that's because you throw it up and it accelerates down. Those are in opposite directions of each other. Another interesting fact is I could also not even break this one in half. If I call the initial and the final velocity, if I knew were the same thing, they were the same value. Let's say if I replaced both with x and I solved for x, I would get, but one is negative, one is positive because they're going opposite directions. So for example, if my final velocity was x and my initial velocity was negative x, if I was to solve for that, I would get 2x is equal to 10 meters per second squared times 1.6. And, or sorry, not 1.6. I would have to replace it for the 3.2 seconds the whole time. And I would get, again, 16 meters per second. So what I want to illustrate by going over those couple examples with this one is there's plenty of ways to solve these problems. As long as you're being physically accurate, you're being conscious about what should be positive, what should be negative, there's a lot of choices here you can make. And all of them will end up being the correct answer as long as you use proper physics. And that can sometimes, make students a little bit worried about it. But it's just something that we're going to get used to. Now, I'm not going to assign any questions at the end of this one because I don't think we're ready to tackle one of these questions by ourselves. However, when we get into class, after we go over the one worksheet that we have left, we're going to be tackling one of these questions and seeing what it's like to answer one of these. So that's everything for today. I hope you have a good one.